Okay, so this is the second part and final part of this lesson. So we're going to be looking at lesson 11/12, which is representing graphics. The first thing that I want you to do is to have a go at doing this socrative here. Click on the link and the room name will be posted on Teams, so you'll be able to see what that is. So it depends on what class you're in. If it's my class, it's D Tracy, which you should know, but if you're in one of the other classes, obviously have a look at Teams to find out what your socrative room name is. And we're going to be working through this. However, before we do so, I'm going to go through a PowerPoint with some information on, which should help you answer the questions. So to start with, it's a term that most of you will have heard and probably know what it is, to be honest. To start with, we need to know what a pixel is. So when you're looking at an image or a video on a screen, it's actually made up of thousands of tiny little coloured dots known as pixels, and it's short for picture elements. Each pixel is represented by a binary number because, as you know, everything in the computer system is stored actually as a binary number. Now you can see on this image over here that each pixel is made up of a combination of some red, some green and some blue. Now, I have actually done this as well. It's quite interesting to do. But if you get a magnifying a microscope and put it over your phone, you will be able to see each of these individual pixels. So if any of you have got like a pocket microscope or a small microscope at home, you could put your phone under and you can see these pixels, and you'll be able to see the different amount of red, green and blue that's appearing on each pixel. So using that information, then we can sort of go forward with the rest of the lesson. So something else that you need to be aware of is something called resolution. So how good, how high quality an image is will depend on the resolution of the image. The resolution of bitmap images is a way of describing how close together, how tightly packed in all of the pixels are. So there's a sort of crude little picture over here, and you can see a nice clear picture of a town over here because it's got 256 pixels, whereas this one, which is 64 pixels, it doesn't really look quite as much like a town. So if you have less pixels packed into a space, it means that you're not going to have as higher quality images. So a 4K screen display is 3840 by 2160 pixels. And HD screens, full HD, you might have also heard something that's called 1080p. That's actually 1920 pixels wide by 1080 pixels high. So that's why it's called 1080p, because of the amount of pixels vertically up the screen that there are. So there's two different types of graphics that we're going to be talking about. The first one is called a raster graphic. Now this is basically a grid, a dot matrix structure that represents all the different pixels. And what happens is, if you were to zoom in or make that image incredibly large, if you were printing out a huge billboard poster, for example, you're going to notice a loss in quality because you've only got a certain amount of pixels, and as you make the image bigger, you start to see those pixels. They also tend to be large in terms of how much memory is required to store them compared to the other type of image, which we'll look at shortly, because it has to store all the bits for every single pixel. And again, that'll make more sense when we've had a look at a few more slides, but they do tend to be large in terms of their file size. So a bitmap image is a type of raster image. You might have heard of bitmap images or JPEG images. Those are all raster images. Then you've got other things like PNGs and GIFs, which are a different type of image called a vector image, but we'll look at that in a second. So this raster graphic here, we've got this picture of a flower over here. You can see some of the pixels. It's not high quality. However, if we make it bigger, you really can start to see the loss in quality there. That's because we've still only got the same amount of pixels, and you can start to actually see them. So more on bitmaps then, in terms of working out how they actually store the information. So here we've got a very basic image of a smiley face, a black and white smiley face. So this is a black and white bitmap image, and for each of these pixels, imagine that each of these boxes is a pixel. We would need 1 bit to represent each pixel, because if I just get my pointer as a pen, this one here, as it's white, is a 0. These are all zeros, and as you can see, we've got it over here as well. This one would be a 0, and then we've got a 1 and a 0. And for each one of these boxes, each one of these pixels, we only need 1 bit. Remember, a bit is a 1 or a 0. So this over here would be our bit map, showing us what each of the colours are. Okay, so this bitmap images can be represented using 56 bits. So you can, if you're not very good at maths, you could count up how many pixels there are. However, we know that this grid is 7 by 8, so 7 times 8 is 56 bits. Now, you might be asked to add some answers as bytes. They sometimes do it to try and trick you out, and also to see if you know what a bit and a byte is. So remember, a bit is a 1 or a 0. A byte is when you have 8 ones or zeros grouped together. So 0, 1, 1, 0, 1, 1, 1, 1. There's 8 bits there, so that's classed as a byte. So what you can do is just divide it by 8, and that will tell you how many bytes you would need. So a byte, remember, is 8 bits. So one of your tasks is going to be asking you to draw out whatever this bitmap image is on the grid that you've got on your OneNote. So using the previous slide, you should be able to do that. There's also an extension question which some of you might want to have a go at. So if we were using a 256 colour palette, how many bits would be required for a full colour image using the grid above? So actually, if we were using 256 colours, how many bits would be required for an image using this up here? So obviously previously we've just used 2 colours, a 1 and a 0, black and white. If you were using 256 colours, how many bits would you need for each pixel, etc.? That's what you need to be thinking about for this question. I'm going to go through the answer to that now, so if you don't want to hear the answer, pause it and go and have a go up to this point, filling out your OneNote. Okay, so the answer to that first task is that there. The answer to the BRD extension is that each pixel would require 8 bits or a byte in order to represent the 256 colours, because you know that from 8 zeros to 8 ones, that can represent 256 different colours. That means for each pixel, you're going to need 8 bits. So I'm going to flick back up to the question. So for this pixel here, you would need 8 bits to store 256 colours. So imagine that this one was, I don't know, red, because I've got the red pen. Maybe the binary code for red is 0, 1, 1, 0, 1, 1, 1, 0. Okay, now it's not, but imagine that it was. We've got 8 bits then that would represent this colour here. We might have a different colour in this one, so we need another 8 bits. Okay, and then doing a bit of maths, we can work out if the grid is 8 by 8, that means that there's 64 pixels. If each pixel, or each 64 pixels, needs 8 bits, that means we need 512 bits in total. So, looking at colour depth then. So to add colour in, like we've just discussed, you're going to need more bits for each pixel, as we've just looked at. Colour depth also allows for a greater range of colour for each pixel, but it means that the file size is going to increase. So instead of it just being 64 bits for that previous image, we ended up needing 512. So you can see that you're going to start to need more space for those images. So in terms of how much space, there's a task on your OneNote that's going to ask you to have a look at colour depth. So here you can see for 1 bit colour, which is black or white normally, 2 colours, you can have a 0 or a 1. So that is then 2 to the power of 1. If we had 2 bits, we could have 0, 0, 0, 1, 1, 0, or 1, 1. So therefore, we have 4 different colours that we could have. Okay, so in this case, we've got 2 to the power of 2 in this case. Now, the way that we're working this out, it's always going to be a 2 here, because binary is base 2. And in terms of what we're putting it to the power of, we're getting that from over here to say that there are 2 bits. So with that, you should then be able to fill out the rest of your table. So for 3 bits, you've got 0, 0, 0, all the way up to 1, 1, 1. And now we've got 2 to the power of 3. And with a calculator, you should be able to work out then how many possible colours there are. So at this point, again, go back to your OneNote and have a go at doing this, because I'm about to put up the answers and nobody likes a cheat. Oh, okay, so as you can see, we've done the first one. We've now got, if we had a 3-bit colour, it means we could have 8 colours. You're starting to get a slightly better quality image there. If we had 4 bits, we've now got 16 colours. 8 bits, 256 colours. Okay, so 8-bit gaming, 256 colours. What we actually tend to use is 24 bits, which is 16.7 million colours. And you can see how exponentially quickly these grow. So that is what we class as true colour, and that allows us to cover as many colours as the human eye can see. So what we use these 24 bits is, we use 8 bits of them for some red, 8 bits of them for some green, and 8 bits of them for some blue. And that is why on a pixel we have that red, green, blue light within each pixel that allows us to make those 16.7 million colours. Okay, so calculating storage again then. So we're going to go back over this again because it is quite important and it does come up quite regularly. So firstly, we need to know the height of the image in pixels. We need to know the width of the image in pixels so that we can work out how many pixels there are in total. And we also need to know what the colour depth per pixel is. So is it 2-bit colour, 16-bit colour, 24-bit colour, etc. So this image here you can see is 10 by 10. So we know we've got 100 pixels. So I've kind of jumped ahead a little bit. We've got 10 by 10. That was a bit weird. And we've also got 100 pixels down here. And we know that the colour depth is 2 bits. We've got 1 bit and 2 bits. Okay. And if you look back, remember that could actually give us 4 different colours. So we've got white, we've got black, we've got dark grey, and we've got light grey. So you can see our 4 different colours in this image. So we now know we've got 100 pixels and we've got 2-bit colour. So we've got our 2 bits. So therefore 100 pixels times 2 bits of colour means that we need 200 bits to represent all of this image. And if you were to count every 0 and 1 in this image, you'd find that there are 200. If the answer is asking you to put it in bytes, remember you need to divide it by 8 because there are 8 bits in a byte. So we would need 25 bytes or 200 bits to represent this image here. So there's another example here which I want you to pause the video and have a go at doing. So do that now. And here is the answer for that, so you can check that you got that right. Notice this time the answer needed to be in bits, bytes and kilobytes. Now, saying that there are 1,000 kilobytes, 1,000 bytes in a kilobyte, which is what we've done down here when we start to get to the maths, and I'll show you in a second, is okay for the exam. There are actually 1,024 bytes in a kilobyte, which I'm sure most of you knew. However, for mathematical purposes, the exam board are happy if you just divide it by 1,000. So, going through the answer then, our image has 80,000 pixels because it's 200 pixels wide by 400 pixels. No, 200 high by 400 wide, so we've got 80,000 pixels. We've got 16-bit colour, so exactly the same as on the previous task. We do our 80,000 times 16, and that gives us 1.28 million bits. Now to work out what that is in bytes, we divide it by 8, so we've got 160,000 bytes, and to find out how many kilobytes that is, which is 1,000 bytes essentially, we divide it by 1,000. So 160,000 divided by 1,000 is 160 kilobytes, so our answer is 160 kilobytes, 160,000 bytes and 1.28 million bits. So mark your own work for that one, please. Right, finally then we're going to have a look at something else called vector graphics. Now these are different from the graphics we've just been looking at, which were raster graphics. So a vector graphic doesn't store the information about every pixel. It's basically a load of mathematical coordinates for each of the lines and colours and shapes within an image. So it tends to be quite a simple image, like a clip art maybe, or just a general geometric shape like a star. The advantage of this is that you can increase these images without losing quality. So you might have found in the past that you can zoom in on certain images and it doesn't lose quality. Certain sort of maybe like fireworks files, PNGs and things like that. Sometimes you can zoom in and it doesn't lose any quality or doesn't pixelate at all, and they tend to use less storage because it's just storing mathematical data. So we've got an image here, and you can see it's just a basic star shape. Now what I can do is I can make that bigger and it doesn't lose quality at all, like the previous picture of a flower did. And that's because it's just storing information mathematically about these shapes. So it might say that this first line starts at position 100 across and 0 down, and the end of this triangle starts, or the second point of this triangle starts at so and so coordinates. And that's how it saves space and also allows you to increase it, because as you increase this, say if I make this bigger by 2, it would just times that number by 2 and that number by 2, etc., so that you can enlarge the image without it losing any quality. Now you don't need to understand the technicalities behind that like I've just explained them. What you need to know is that a vector graphic can be scaled up without loss of quality, and they take up less storage. So you can make them bigger without losing quality, and you don't have as much storage space requirements. Now I know I said finally on the first one, that's because I forgot about metadata. So finally, metadata. This is a term that is often referred to as data about data. Essentially, when you have an image file, for example, you have metadata along with it, and this is information about the actual image, so data about the data. Often that will be things like the height, the width, the colour depth, the geolocation that the photograph was taken, the type of camera it was taken with, the file name, lots of different things that can be stored alongside an image. Now you can see that metadata if you right click on any image file on your computer or on your phone, and you go to properties, or you go to details, or you go to about, depending on the device that you're using, and you'll be able to see all the information that's stored along with your image. And we're jumping ahead a lesson, but if we were also talking about metadata for sound files, it might have things like the length of it, the bit rate, the artist, the album, the track number, the genre. Those things are stored about audio or music files. So that is what we class as metadata. Now that should have covered everything that you're going to need to complete lesson 11/12, so you can make sure you work your way through this. On the extension task, if you can't open this, don't worry about it. It's just it's not going to affect your learning as such. This was just to give you a chance to have a go at creating an image over here. But if you can't open that, there's not much I can do, unfortunately. Okay, so there's an exam question for you to have a go at the end, and you don't need to worry about doing the homework. Don't do the homework. Okay, right. Hopefully see you all back at school soon. Take care, everyone.